This video will serve as an introduction to differential equations. We'll start by considering a mass attached to a spring. We then pull the mass down, and when we release it, it'll start to oscillate. I want you to think about the block's height as a function of time. So let's plot it. Our horizontal axis represents time, and the vertical axis will represent the height of the block, which we'll call y of t. So let's go ahead and plot our function. Our goal is to figure out what this function y of t is. So let's represent y of t in a different way. We're going to include a horizontal axis on the other side of the block. And now I'll include an arrow that represents y of t, the height of the block. Now I need you to think about the acceleration of the block, which is y double prime of t. How would you represent the acceleration with an arrow? Well, let's think about it. So at the bottom, the acceleration is pointing up, and at the very top, the acceleration is pointing down. And it turns out for this system, our acceleration is represented like this. I want to point out that it appears that y double prime of t is the negative of y of t. So let's write this out. The way we would write out this equation is y double prime of t is equal to negative y of t. And this is called a differential equation. We've written the function y in terms of its derivatives. Now, just knowing that this mystery function y of t satisfies this differential equation isn't enough to know exactly what y of t is. For example, here's one solution to the equation. Y of t is equal to cosine of t. And what does it mean that this is a solution to this differential equation? Well, let's compute y prime of t. We get negative sine t. And then y double prime of t, we get negative cosine t, which is equal to negative y of t. So this means that it's a solution to the differential equation y double prime of t is equal to negative y of t. But there are also other solutions. For example, y of t is equal to 7 times sine t. And let's compute again. So we have y prime of t is equal to 7 times cosine t, and then y double prime of t is equal to negative 7 sine t. So again, just knowing the differential equation isn't enough to specify the solution. We need more information, something called an initial condition or a boundary condition, and I'll show you what I mean. This time we'll look at two mass spring systems. And again, we'll pull down the blocks, but this time we're pulling them down different amounts. We've stretched the one on the left farther down than the one on the right. Once we release them, we see that they're oscillating differently. So let's graph both of their heights as a function of time. So we'll build our plane again, with horizontal axis time and the vertical axis representing the height. And when we plot the functions, we see there's some similarity. They're both some sort of wave, but there's also a difference. The one on the left seems to be a much taller wave than the one on the right. Now I want to point out a property that both functions have. If we include another horizontal axis to the right, and again we're going to plot an arrow representing the height of the function. The arrows representing the heights are different, but if we include the acceleration, in both cases, y double prime of t is equal to negative y of t. Even though the functions are different magnitudes, the one on the left is much larger than the one on the right, we still have this relation between the function and its second derivative. Both systems satisfy the differential equation y double prime of t is equal to negative y of t. and yet the resulting function is different. Well, this has to do with the very beginning. Remember, we stretched them out different lengths, so their initial height was different. And there's another piece of information which happens to be the same in this example, was their initial speed, which was 0. And these two pieces of information are called initial conditions. And if you told me that a system satisfied this differential equation, y double prime is equal to negative y of t, and you also told me the initial value of y of 0 and y prime of 0, I could tell you the exact solution. This information together completely specifies this system. We're going to keep looking at this differential equation y double prime of t is equal to negative y of t. And we can write a general solution to it as y of t is equal to c1 cosine t plus c2 sine t. And I'll show you that it's a solution. So if we compute y prime of t, we get negative c1 sine t plus c2 cosine t. Then y double prime of t is equal to negative c1 cosine t minus c2 sine t, which is equal to negative y of t. So this satisfies the differential equation. But now we're going to impose some initial conditions. So let's set y of 0 equal to 5 and y prime of 0 equal to 0. Let's see how this affects c1 and c2. So if we plug in the initial conditions, let's compute y of 0. And using our formula, that should be equal to c1 cosine of 0 plus c2 sine of 0. And cosine of 0 is 1, sine of 0 is 0, so we get c1 is equal to 5. If we compute y prime of 0, we get negative c1 sine 0 plus c2 cosine 0, which is equal to c2, which the initial condition tells us this should be equal to 0. Then finally, plugging in this value, we get that the solution to this differential equation with the boundary conditions is y of t is equal to 5 cosine t. And that's where I'm going to end this video.